There are many moral issues with sacrificing animals to evaluate the potential toxicity of materials. We can gain information about the potential risk to human health without harming animals if we think in a different way. This poster summarizes a method that can be used to evaluate carcinogenic potential of mineral wool fibers without harming animals. This study was conducted to determine the in vitro biosolubility of a mineral wool. What is mineral wool? Mineral wool fibers are amorphous glasses that are used in the building industry for insulation and other purposes. To manufacture mineral wool, molten glass, stone, or slag, and other raw materials are heated and spun into very thin fibers that are flexible. Slag wool has desirable insulative, fire-resistant, and acoustical properties, which is why it is an ingredient in a variety of common construction materials. When working with construction materials, it is possible that some particulates may become released into the air. In the case of products containing mineral wool, the airborne particles for consideration are those that are small enough to be considered respirable. This size classification represents particles of which some fraction could potentially be trapped in the gas exchange region of the lung. For many products containing mineral wool, only a small, if any, portion of the mineral wool fibers are fine enough in size to be considered respirable. What would happen if mineral wool fibers were deposited in the deep regions of the lung? Prior studies using animals have shown that potential cancer risk has not been established for mineral wool fibers that have relatively high biosolubility. The degree of biosolubility of mineral wool is related to the chemical composition of the fiber. USG has teamed with RJ Lee Group, an independent testing laboratory, to obtain information related to the potential rate of the biosolubility of fibers through an in vitro test that uses simulated lung fluid. Fine size fractions of a specific slag wool fiber were isolated and test fluid was slowly pumped over the fibers. Testing was conducted in a chamber that was maintained at human body temperature. Dissolution rates were established based on elemental analysis of eluent samples obtained at different time periods. The total dissolution rate as a function of gravimetric weight loss was also determined. The Fiber 22 dissolution rates determined using the UREMA protocol are consistent with other test results on the same fiber. These results can be correlated to past in vivo studies where no irreversible damage to the lungs was observed.